So here we go. So my name is Simo Särkkä. I'm indeed a professor with Aalto University, and I'm also leading the AI for X program with the Finnish Center for Artificial Intelligence. And my talk is a general talk about optimizing energy efficiency with AI and energy efficient AI systems. So how to optimize AI to be energy efficient as well. Indeed, as Laura already briefly mentioned, there's a duality in AI energy efficiency, which refers to these two aspects. So that there's one aspect of using AI to improve energy efficiency. So we might have the AI system, and then we are using that AI to actually optimize, for example, the energy production or energy consumption in some industrial processes. And so they are typically data-driven methods aiming to improve the energy efficiency of certain kinds of processes. The methodologies are prediction methods, finding bottlenecks, optimization. So they are actually quite classic uses of AI, or more specifically machine learning methods and other data-driven methods. But then the other side of the duality is making AI more energy efficient. So because the use of AI itself consumes a lot of energy and other resources like water, to cooling and that kind of things. And there are all kinds of predictions. So, for example, one of them quoted a lot nowadays is that the AI industry could consume as much energy as the country of size of Netherlands by 2027. And that's anyway the order of magnitude that we might be expecting in worst case if you don't do anything. So that there's this red line on the right shows that actually the AI itself consumes energy as well. And we want to balance it so that these benefits are larger than the consumption itself. But for the first part of the duality, so how can we use AI to improve energy efficiency? So indeed, we can optimize the generation of the energy and distribution of the energy. To use data-driven methods for optimizing the production, like wind, sun-based production of energy, or then optimizing the classical power plants. And then, like for that purpose, we also need to enhance the monitoring and prediction of the energy consumption for distribution, for example. So where to send the energy and where we shouldn't send the energy, not to lose anything. And then the use of multiple data on the demand, weather, and such other data sources as well to actually do the optimization. So that's also one promising application of AI methods. And then another side is making the industrial processes and other processes more energy efficient. For example, by analyzing the data from the processes and the energy efficiency, and then finding the bottlenecks and then optimizing the aspects so that there's an intelligent control and optimization happening on the fly in the process. Then another aspect is the management of energy efficiency in buildings, because all the factories are in buildings, so also the energy efficiency of that is important. And then optimizing the logistics and transportation, so transporting materials from one place to another is costly also in energy wise, and then that can be optimized by careful optimization and data analysis as well. Then enhancing the fuel efficiency in air, marine, and land transportation. Well, that's actually part of the optimization of the logistics, but it is more general. So that can also be used by using data-driven AI methods. So what kind of AI is needed for this first part of dual, so optimizing? So it's actually got classic use of data-driven methods, so AI methods. So we analyze the data, make a model, and then optimize. And so in the analysis, we could, for example, analyze data patterns, so collecting a lot of data from sensors, centering the processes, and then we find the data patterns in one way or another, and then try to improve based on these data patterns. So we can use energy efficiency data, or then some physical models of the energy efficiency or energy consumption as part of this analysis and modeling. And Typical use or tools for this purpose are something called digital twins, which can be used to model and simulate the energy efficiency. And surrogate models, so they are like light versions of digital twins, typically used to mimic the process so that we can have a more lightweight simulation of the system instead of the full-scale twin. And optimizing over the learned models, so that's a typical use case for the surrogate models or digital twins. So once we have a system, so if we set the parameters, then we know what the output is. So we can optimize over the parameters to make the system more efficient. And then like sometimes we want to jointly analyze the data and learn the process and also optimize. So this is also possible by using AI methods, like combining reinforcement learning type of methods with neural network type of methods. And then design of experiments is related to optimization. So we actually optimize some kind of process steps so that we both learn and optimize the system in an optimal manner. But then the other side. So we have two-party duality, so how to use AI to improve energy efficiency, but we also need the AI to be energy efficient. That's because nowadays already the carbon footprint of AI is no longer negligible. And so roughly maybe half of that actually comes from the footprint of the hardware. So the computers, network elements, data storage, CPUs and GPUs. But then there's well, we can do something on that. But then the other part is consumed, or the other part is the consumed energy of the AI methods themselves when they are running. And indeed, already nowadays, the AI consumes a significant amount of energy. In particular, training of the models requires a large number of GPU and CPU hours. And so that applies to, well, large language models, and then like image classification models, and then also like image generation models. But then especially inference, like not only training, but also the inference takes a lot of power nowadays. That's a new thing that has actually become active in a couple of last years. So for example, these transformer models, which are the basis of the large language models, they actually need a lot of energy also to run. So when you ask something from the ChatGPT, it takes a lot of computational power to actually give the answer. And that's like doing the inference in transformer models. And the same applies to so-called diffusion models, which are the basis of the image generation in tools like Midjourney and DALL-E. And they also need a huge amount of resources in GPUs to be able to generate the images, even though they have been trained before. And so the main energy gluttons are the large deep learning models, especially foundation models, both in training phase and also in the continuous inference phase. So what can we do? So one approach is to develop more energy efficient hardware. So more energy efficient GPUs, TPUs, FPGA devices. And then we can use distributed computing, so we can place the computational devices in such places which are somehow more energy efficient. For example, we don't need to have so much cooling, or we have some efficient energy resources available. Or then use edge computing, which means that like distributing the computing to smaller devices and be near the data, near the sensors. And well, actually clouds in suitable locations is an example of distributing the computing based on the energy availability. And then, so once we have the hardware, then we need to utilize this hardware in more energy efficient way. So algorithms that use the efficient GPUs effectively, like parallel computing methods, algorithms that operate in distributed environment, distributed computing methods, energy optimal scheduling and distribution of the computations. So these are the tools that can be used to, or methods that can be used to utilize the hardware that we have. But then, okay, so what actually costs in the computations? Well, it's basically it's the computations as such. So it's the well, one part is the floating point operation. So the number of floating point operations that the computations take. So how many additions and summations and matrix multiplications we need to do to be able to do the inference or trading. This floating point operations is also directly proportional to the amount of data. So actually, roughly speaking, that's a very rough estimate, but it's anyway increasing with the number of data. So, and also that the data, there's also like a transferring the data to one place to another actually takes resources, but they are, so it's even more than directly proportional to the amount of data in reality. But anyway, so the number of floating point operations and the amount of data are the things which can be used as proxies for energy efficiency at least. And it also depends on the number of bits. So there has been a lot of discussion about like using just a couple of bits for doing the computation so that it can be done in a smaller computer. So that is actually one relevant issue here as well. So basically one solution is to reduce the amount of computations and data. It's not simple at all, but in high level, that is a solution to the problem. So there are some ways to do that. So what people have been proposing is, for example, reduce the number of iterations regarding to tune hyperparameters. So that is assuming that we have hyperparameters in the method, but that's very typical in the deep learning method is that we have certain hyperparameters that need to be tuned, and that takes a lot of computational power. And one way is to try to improve in that. And another completely different way is to add the power consumption to this set of parameters to be optimized. So in particular, these for the inference phase, it's possible to do that. So we actually try to optimize the inference phase so that it doesn't take too much energy in the end. And then one bit dull approach is to avoid these deep learning models and use classic machine learning. That is a bit of like going backwards to the past, because like of course there used to be this classic machine learning methods which didn't work so well as these deep learning models. But now the problem is that the deep learning models are computational so heavy so that they consume all the energy. So maybe we need to have a balance between these two. And then, well, reduce the size of the data set is one way. The problem is that it's not that simple. So because these deep learning models are based on the huge data, so that's why they work so well. So we need quite good algorithms to be able to actually cope with that problem. And yes, so the problem is that if we think about just optimizing the precision or accuracy of a method, so in a sense, so the optimal way is to use maximum amount of energy. So whatever energy we ever have in the universe, we should use it for the computations, and that gives the best results. But that's not good. But then on the other end, the minimal energy without any constraint is not performing any computations at all. So we have this 0 and infinity. And so the problem is to find some kind of a Pareto trade-off or other trade-off between having this sufficient accuracy, but then sufficient energy efficiency. It's a problem of balance. And there already are some approaches to accomplish that in literature. Ideas are like removing neurons from neural networks, which affects both accuracy and energy consumption. So you can balance between those. And then optimizing the energy while keeping accuracy loss within a negligible margin. And then in the classic side, for example, decision trees are very energy efficient. So for the problems where you can use decision trees, then they are going to be more energy efficient. Because the problem is that who wants to use decision trees nowadays? So they are not the best models that exist. But then in this direction, there are also like a lightweight convolutional neural network designed for power efficiency in mind. So they are like, actually class of algorithms that utilize the hardware energy efficiently. Other issues that matter. So we need to be able to estimate the energy efficiency. So it's important and challenging. So not only estimate, but also predict, so that we can do that as a design criterion in either algorithm or hardware or system. And indeed, the choice of the algorithm matters a lot. So there's a huge difference whether it's like a convolutional neural network or linear regressor. So, and anyway, between these, there's a large continuum of different kinds of methods. And the choice of library also matters. PyTorch, JAX, TensorFlow, they have different properties. So some take more energy in the training phase, and some take more energy in the inference phase. And then also like whether you use like a just-in-time compiling or compile beforehand, and so on. So that also affects quite a lot. Data collection, delivery, pre-processing, that also affects. And then how to do feature selection or feature learning, like in deep learning, or whether we use subsampling or not. That also affects. Then if we go to distributed computing models or these parallel computing models, then the network architecture, the cost of communications will matter. Then how we actually distributed the computing between the computers. So as a conclusion, there are two aspects in the energy efficiency of AI, or it's like a dual problem. So one point of view is using AI to improve energy efficiency. So indeed, like how to optimize, for example, industrial processes to be more energy efficient, how to optimize their energy network, energy production. There are various ways to do this. But then the other important aspect is how to make AI itself more energy efficient. That's important because the carbon footprint of AI is no longer negligible. And so the AI training and inference use a lot of energy already nowadays. So OpenAI and Midjourney and other companies are consuming quite a lot of energy. And one way is to make hardware more efficient. And there are indeed multiple approaches to do that. Then once we have the hardware, so then we need to make the algorithms to use the hardware more efficiently. So the bulk old algorithms will not be energy efficient just by running them in the new hardware, but we need to also modify them. And then in high level, we can also improve the algorithms to use less computations and less data, which is of course like easier said than done. But these would be the current ways to make AI more energy efficient. And here are a couple of references from last years. There are more, but thank you for listening.